Hello there. Tonight we're going to drift through the cosmos, through our home galaxy, the Milky Way. A vast spiral of stars and dust and mysteries that we're only just beginning to understand. For all the telescopes we've pointed at the sky, for all the missions we've sent into space, the Milky Way still holds secrets that no one can fully explain. Some are about the structure itself, how it formed, why it looks the way it does. Others are about what's hidden inside it, dark matter, black holes, entire regions we can't even see. These unanswered questions remind us that even our own cosmic neighborhood is far stranger than we imagine, and that we're explorers in a galaxy far bigger and more complex than we can yet comprehend. If you enjoy drifting off to cosmic wonders, feel free to like and subscribe or simply share your thoughts down in the comments. It helps others find their way here too. But for now, let these mysteries of the Milky Way carry you. And if you're ready, let's begin. We still don't know exactly how old the Milky Way is. It seems like a basic question, right? How old is our galaxy? And yet the answer is surprisingly uncertain. Astronomers can estimate, sure. They look at the oldest stars they can find, measure their ages, and work backwards. Most estimates put the Milky Way somewhere around 13 billion years old, maybe a bit more, maybe a bit less. But the problem is that galaxies don't just form all at once like a switch flipping on. They grow gradually, messily, over billions of years. The Milky Way probably started as smaller clumps of stars and gas that merged together over time. So when exactly did it become the Milky Way? When it had a certain number of stars? When it developed spiral arms? There's no clear birth certificate. And the oldest stars we can see might not even be the original ones. Some could have formed elsewhere and been captured later. Others might have been destroyed in collisions or swallowed by black holes. The galaxy has been recycling material for billions of years, so tracing its exact age is like trying to date a ship that's had every plank replaced multiple times. Some researchers think parts of the Milky Way could be even older than 13 billion years, dating back to when the universe was less than a billion years old. Others suggest the modern structure we recognize only took shape much later, maybe 8 or 9 billion years ago. The truth is probably somewhere in between, but without a time machine or a perfect record of ancient starlight, we're left guessing. Every measurement we make gives us a slightly different answer, and the uncertainty reminds us that even asking when something began can be more complicated than it sounds. The Milky Way has a huge halo we can barely detect. When you picture the Milky Way, you probably imagine the bright spiral disk, the dense band of stars stretching across the night sky. But that visible part is only a fraction of the whole thing. Surrounding the disk is something called the galactic halo, a vast spherical region that extends far beyond what we can easily see. This halo is filled with old stars, globular clusters, and probably a lot of dark matter, but it's so diffuse and faint that detecting it is incredibly difficult. The stars out there are spread so thin that you could travel light years without encountering one. Some of them are among the oldest in the galaxy, ancient suns that formed billions of years ago when the universe was young. They orbit the galactic center in long elliptical paths, passing through the disk occasionally, but spending most of their time in the lonely outer regions. Why is the halo there? Astronomers think it formed from the leftover material after the main disk came together, or maybe from smaller galaxies that merged with the Milky Way early on. Some of those ancient stars could be survivors from those smaller galaxies, captured and scattered into the halo. But measuring the size and mass of the halo is tricky because it's so faint. We know it's there because of gravitational effects and the motion of stars, but mapping it in detail is still ongoing. Some estimates suggest the halo could extend as far as 1 million light-years from the galactic center, far beyond the visible disk. That's enormous. And if dark matter is concentrated in the halo, which many scientists suspect, then the halo could contain more mass than all the visible stars combined. It's a ghost structure, invisible but immensely important, holding the galaxy together with its gravity. Without it, the Milky Way might not even exist in the form we see today. We don't know how many stars are actually in the Milky Way. This sounds strange because you'd think we could just count them, right? But the Milky Way is huge and filled with dust and gas that block our view of large sections. Most estimates say there are between 100 billion and 400 billion stars in the galaxy. That's a pretty wide range. The uncertainty comes from several factors. First, we can't see the whole galaxy from our position inside it. We're located about halfway out from the center in one of the spiral arms, and there's a lot of material between us and the core that obscures our view. Second, many stars are too faint to detect individually, especially small red dwarfs, which are the most common type of star but also the dimmest. We can see the bright ones easily, but the faint ones blend into the background glow. Third, stars are constantly being born and dying, so the total number changes over time. New stars form in nebulae while old ones explode as supernovae or fade away as white dwarfs. The galaxy is dynamic, not static. To estimate the total number, astronomers use models based on the mass of the galaxy and assumptions about the distribution of diffees, rent types of stars. But these models depend on measurements that have their own uncertainties. Some regions of the galaxy are denser than others. The central bulge is packed with stars while the outer edges are sparse. The spiral arms contain more young, bright stars, while the halo has older, dimmer ones. All of this variation makes it hard to pin down an exact count. And then there's the question of what counts as part of the Milky Way. Do we include stars in satellite galaxies like the Magellanic Clouds? What about stars that are being pulled away by gravitational interactions? The boundaries are fuzzy, so when someone says there are 200 billion stars in the Milky Way, they're giving their best guess, but the real number could be quite different. It's a reminder that even basic facts about our galaxy remain surprisingly uncertain. The center of the Milky Way is hidden behind dust. If you look toward the constellation Sagittarius on a dark night, you're looking toward the center of the galaxy, but you can't actually see the core because there's too much dust and gas in the way. Visible light gets absorbed and scattered by all that material, leaving the central region dark and mysterious. For most of human history, we had no idea what was at the heart of the Milky Way. It wasn't until astronomers started using infrared and radio telescopes, which can penetrate dust, that we began to get a clear picture, and what they found was astonishing. At the very center, there's a supermassive black hole called Sagittarius A star, or SGR-A star for short. It's about 4 million times the mass of the Sun, sitting quietly at the galactic core. Most of the time, it's relatively inactive, not consuming much material, but occasionally something gets too close and we see a flare of radiation as it's torn apart and swallowed. Surrounding the black hole is a dense cluster of stars, packed so tightly that they orbit the black hole in just years or decades instead of millions of years, like our Sun does around the galaxy. These stars move incredibly fast, some reaching speeds of thousands of kilometers per second. By tracking their orbits, astronomers can measure the mass of the black hole and confirm that it's really there. But even with modern telescopes, we can only see a small fraction of what's happening at the center. The dust still blocks a lot of detail, and the region is so crowded and chaotic that disentangling individual objects is difficult. There are probably millions of stars within a few light years of the black hole, along with clouds of gas, remnants of old supernovae, and who knows what else. Some scientists think there could be thousands of smaller black holes orbiting near the center, left behind when massive stars exploded. Others speculate about strange stellar populations or unusual objects we haven't detected yet. The center of the Milky Way is a place of extremes where gravity is intense and the environment is hostile. And because we can't see it directly in visible light, much of what's happening there remains hidden, waiting to be discovered. The Milky Way has spiral arms, but we're not sure how they work. The spiral structure is one of the most recognizable features of the galaxy. Those graceful arms winding out from the center like a cosmic pin they are, astronomers still don't fully understand how spiral wheel. But despite how prominent arms form or why they persist, the problem is that galaxies rotate, but not like a solid disk. Stars closer to the center orbit faster than those farther out, a phenomenon called differential rotation. If the spiral arms were just made of stars, they should wind up tighter and tighter over time until they disappear, but they don't. The arms remain distinct for billions of years, which suggests they're not just collections of stars, but something more like waves moving through the disk. One theory is that spiral arms are density waves, regions where stars and gas are temporarily compressed as they pass through. Imagine a traffic jam on a highway. Cars slow down as they enter the jam and speed up as they leave, but the jam itself stays in roughly the same place even though the cars are constantly moving through it. Spiral arms might work the same way, with stars and gas entering the arm, getting compressed, and then leaving again while the arm structure remains. This would explain why the arms persist without winding up. But there are problems with this theory too. For one thing, density waves should cause more for information in the arms than we actually observe. And the details of how these waves form and maintain themselves are still unclear. Some simulations show spiral arms forming naturally from gravitational instabilities in the disk, while others suggest they're triggered by interactions with nearby galaxies or disturbances from the central bar. The Milky Way has a bar-shaped structure at its center, and this bar can drive spiral patterns in the disk through resonances and gravitational interactions. But exactly how this works in our galaxy is still being studied. We're also not entirely sure how many spiral arms the Milky Way has. Maps of the galaxy show anywhere from 2 to 4 major arms, depending on which tracers you use. Young bright stars outline certain arms, while older stars and gas show different structures. It's possible the galaxy has multiple overlapping patterns, or that the arms are more irregular and fragmentary than we think. From our position inside the disk, it's hard to get a clear view of the overall structure, so we're left piecing together clues from different observations and hoping they all fit together. We don't know how much dark matter is in the Milky Way. Dark matter is this mysterious substance that doesn't emit light or interact with normal matter except through gravity. We can't see it directly, but we know it's there because of the way galaxies move and the way they hold together. Without dark matter, the stars in the outer parts of galaxies would be moving so fast they'd fly off into space. but they don't. Something invisible is providing extra gravity to keep them bound. In the Milky Way, astronomers estimate that dark matter makes up about 80 or 90% of the total mass. But that's an estimate. The exact amount is uncertain because we can't measure it directly. We can only infer its presence from the motion of stars and gas. By measuring how fast stars orbit the galactic center at different distances, scientists can calculate how much mass must be present to produce those speeds. And the numbers don't add up if you only count the visible matter. There has to be a lot more mass out there, and we call it dark matter. But how much exactly, and where is it distributed? Some models suggest it's concentrated in a roughly spherical halo around the galaxy, with the density decreasing as you move farther out. Others propose more complex distributions, with clumps and streams of dark matter flowing through the galaxy. There could even be dark matter passing through the Earth right now, particles moving through us without us noticing. Experiments deep underground are trying to detect these particles, but so far no one has succeeded. The nature of dark matter is one of the biggest mysteries in astrophysics. Is it made of particles we haven't discovered yet? Is it something else entirely, and how does it interact with normal matter, if at all? In the Milky Way, dark matter is like a hidden scaffolding, holding everything together but remaining completely invisible. We can measure its effects, but we can't see the thing itself. We've tried building detectors to catch dark matter particles, and so far, nothing. These experiments are usually set up deep underground to shield them from cosmic rays and other interference. They use incredibly sensitive instruments that can detect the tiniest interaction between a dark matter particle and normal matter. But after years of searching, there's been no confirmed detection. Either dark matter particles interact so weakly with normal matter that we can't detect them with current technology, or maybe we're looking for the wrong thing entirely. Some scientists think dark matter might not be particles at all, but something else. Maybe it's a modification of gravity that we haven't understood yet. Maybe the laws of physics work differently on galactic scales than we think. It's frustrating because dark matter is supposed to be everywhere, including right here on Earth, but we can't grab it, can't see it, can't even prove what it is. And in the Milky Way, it's the majority of the mass, the stars, the gas, the planets, all the stuff we can see and measure. That's the minority. The galaxy is mostly made of something we know almost nothing about. The center of the Milky Way might have thousands of black holes. At the very heart of the galaxy sits Sagittarius A star, a supermassive black hole with a mass of about 4 million suns. But it's probably not alone. Astronomers think there could be thousands, maybe tens of thousands, of smaller black holes orbiting near the galactic center. These would be stellar mass black holes formed from the deaths of massive stars. Over time, they'd sink toward the center of the galaxy due to a process called dynamical friction, where interactions with other stars and objects gradually slow them down and pull them inward. So you'd expect a concentration of black holes near Sagittarius A star, but we can't see them. Black holes don't emit light, so unless they're actively pulling in material and creating bright X-ray emissions, they're invisible. Some of these black holes might have companion stars, and we can detect those systems through the X-rays they produce. But many, maybe most, are probably isolated, just drifting silently in the crowded center of the galaxy. Finding them is incredibly difficult. You have to look for their gravitational effects, like the way they bend light from stars behind them, or the way they perturb the orbits of nearby objects. A few candidates have been found, but we're nowhere close to knowing the actual population. It's possible there are thousands of black holes within a few light years of Sagittarius A star, and we just don't know they're there. The center of the galaxy is so dense and chaotic that picking out individual black holes is like trying to find a specific grain of sand on a beach. And these black holes aren't just sitting there doing nothing. They interact with each other, sometimes colliding and merging to form even larger black holes. Those mergers release gravitational waves, ripples in space-time that we can detect with instruments like LIGO and Virgo. Some of the gravitational wave events we've detected might be coming from black holes in the centers of galaxies like ours. But again, it's hard to be sure. We're not sure how the Milky Way will interact with nearby galaxies. The Milky Way isn't isolated. It's part of a group of galaxies called the Local Group, which includes Andromeda, the Triangulum Galaxy, and a bunch of smaller dwarf galaxies. And these galaxies are all moving relative to each other. The Milky Way and Andromeda are actually on a collision course. In about 4 billion years, they're expected to merge, creating a giant elliptical galaxy that some people have nicknamed Milkomeda. But the details of this merger are still uncertain. Will it be a head-on collision or more of a glancing blow? How will the stars, gas, and dark matter and what will happen to the solar system during both galaxies interact? And all this, simulations suggest that when the two galaxies collide, won't actually hit each other. Space-side, the stars themselves, is so vast and stars are so small relative to the distances between them that direct collisions are extremely unlikely. Instead, the galaxies will pass through each other and their gravity will distort both of them, pulling out long tails of stars and gas. Over time, the two galaxies will merge into a single, larger galaxy. But the solar system might get flung out into intergalactic space during the chaos, or it might end up in a completely different part of the merged galaxy. We don't really the Milky Way know. And before it and Andromeda collide, there are smaller interactions happening. The Milky Way is already in the process of absorbing some of the dwarf galaxies in the local group. The Sagittarius dwarf ellipse is being Tornicle Galaxy, for example, apart by the Milky Way's gravity, and streams of stars from it are scattered across our sky. This kind of thing has probably happened many times in the past, with the Milky Way growing by consuming smaller galaxies. So the galaxy we see today is partly built from the remnants of other galaxies. And it's still happening. The future of the Milky Way is tied up with these interactions, and we can't fully predict how it will all play out. The Milky Way's halo might be full of ancient stars we haven't found yet. Beyond the main disk of the galaxy is something called the galactic halo, a roughly spherical region that extends far out into space. The halo contains old stars, globular clusters, and probably a lot of dark matter. But it's so sparse and spread out that we don't have a complete picture of what's there. Some of the stars in the halo are incredibly old, dating back to the earliest days of the galaxy. These are called population 2 stars, and they're interesting because they formed when the universe had very few heavy elements. Most of the elements heavier than hydrogen and helium are created inside stars and spread through space when those stars die. But the first stars didn't have any of that. They formed from almost pure hydrogen and helium. Over time, as stars lived and died, they enriched the galaxy with heavier elements, and later generations of stars incorporated those elements. So by studying the oldest stars, we can learn about the early universe and the first generations of star formation. But finding these stars is hard. They're faint, they're scattered over a huge volume of space, and there's a lot of other stuff in the way. Astronomers have found some very old stars in the halo, including a few that might be among the oldest stars in the universe. But there are probably many more out there that we haven't detected yet, and some of them might have unusual properties or compositions that could teach us new things about the early universe. The halo is also a place where we might find clues about the Milky Way's formation. Did the galaxy form from a single collapsing cloud of gas, or did it grow by merging with smaller galaxies? The distribution and motion of stars in the halo can help answer that question. If the Milky Way formed through mergers, we'd expect to see streams of stars with different motions and compositions, left over from the smaller galaxies that were absorbed, and we do see some of that. But the full story is still being pieced together. The Milky Way might have a warp in its disk. If you imagine the galaxy as a flat disk, like a record or a pancake, you'd expect it to be more or less flat all the way out to the edge. But recent observations suggest that the outer parts of the Milky Way's disk are warped, bending up on one side and down on the other. This warp is subtle, and it's hard to measure because we're inside the galaxy, but it seems to be there. Why would the disk be warped? One possibility is that it's caused by interactions with other galaxies or with dark matter structures in the halo. If a smaller galaxy passed close to the Milky Way, its gravity could have pulled on the disk and created a warp. Or maybe the dark matter halo itself isn't perfectly spherical, and its uneven distribution is causing the disk to bend. Another idea is that the warp is related to the infall of gas from outside the galaxy. If gas is falling onto the disk at an angle, it could cause the outer parts to tilt. But we don't know for sure. The warp is one of those things that's been observed but not fully explained. And it might not be unique to the Milky Way. Other spiral galaxies also show warps in their disks, so it might be a common feature. But understanding why it happens and what it tells us about the galaxy's history and dynamics is still an open question. The Milky Way is not a perfectly symmetric, perfectly flat disk. It's messier than that. It has irregularities and asymmetries that hint at a complex history of interactions and evolution. We don't know if there are other intelligent civilizations in the Milky Way. This is one of the biggest questions in all of science. Are we alone in the galaxy, or is there other intelligent life out there? The Milky Way has hundreds of billions of stars, and many of those stars have planets. Some of those planets are in the habitable zone, where conditions might be right for liquid water and potentially for life. So statistically, it seems like there should be other civilizations out there, but we haven't found any evidence of them. We've been listening for radio signals from extraterrestrial civilizations for decades, and we've found nothing. We've looked for signs of advanced technology, like megastructures or unusual light patterns, and we've found nothing. This is sometimes called the Fermi paradox. If the galaxy is so big and so old, and if life is at all common, then where is everyone? There are lots of possible answers. Maybe intelligent life is extremely rare, and we're the only ones, or one of very few. Maybe intelligent civilizations tend to destroy themselves before they develop the technology to communicate across the stars. Maybe they're out there, but they're not trying to contact us, or they're using communication methods we don't recognize. Maybe they're so advanced that we're like ants to them and they don't bother with us. Or maybe space is just so vast and the distance is so great that even if there are other civilizations, we'll never detect them or meet them. It's also possible that we're just not looking in the right way, or that we haven't been looking long enough. The universe is billions of years old, but we've only been searching for extraterrestrial signals for a few decades. That's nothing. Maybe if we keep searching for a few more centuries, we'll find something, or maybe we won't. The question is still open, and it might be one of those questions we never answer. But it's fascinating to think about. Somewhere out there in the Milky Way, there might be another planet with life, maybe even intelligent life, looking up at their night sky and wondering the same thing we are. The Milky Way's magnetic field is complex and not fully understood. Like Earth, the Milky Way has a magnetic field, but it's much weaker and much more complicated. This magnetic field threads through the gas and dust in the galaxy, influencing how that material moves and how stars form. Magnetic fields can provide support against gravity, slowing down the collapse of gas clouds and affecting the rate of star formation. They can also guide charged particles, like cosmic rays, along specific paths through the galaxy. But measuring the Milky Way's magnetic field is difficult. We can't see magnetic fields directly. We have to infer them from the way they affect other things, like the polarization of light from distant stars or the emission from interstellar gas. These observations give us a rough picture of the magnetic field, but the details are fuzzy. We know the field has a large-scale structure, probably aligned with the spiral arms, but there are also small-scale variations and turbulence. The strength of the field varies from place to place, and its direction can change. And we're not entirely sure how the magnetic field is generated and maintained. On Earth, the magnetic field is produced by the motion of molten iron in the planet's core. But in a galaxy, there's no single core. The magnetic field is probably generated by the motion of ionized gas and the rotation of the galaxy through a process called a dynamo. But the details of how this works in the Milky Way are still being worked out. Some simulations suggest that the magnetic field is constantly being stretched and twisted by the galaxy's rotation and by turbulence in the gas. Other models propose that the field is maintained by the collective motion of many small-scale magnetic structures. It's a complicated problem, and we don't have all the answers yet. Understanding the magnetic field is important because it affects so many things in the galaxy. It influences star formation, it shapes the structure of the interstellar medium, and it plays a role in how cosmic rays propagate. Cosmic rays are high-energy particles, mostly protons, that zip through the galaxy at nearly the speed of light. They're accelerated by supernova explosions and other violent events, and then they travel along magnetic field lines, bouncing around the galaxy for millions of years before eventually escaping into intergalactic space. The magnetic field acts like a maze for these particles, guiding them in complex paths. And cosmic rays, in turn, can affect the magnetic field and the gas they pass through. They can heat the gas, ionize it, and even influence how it collapses to form stars. So there's this whole interconnected system of magnetic fields, cosmic rays, and gas, all influencing each other in ways we're still trying to understand. Some researchers think the magnetic field might even play a role in the formation of the spiral arms or in the dynamics of the galactic halo. But we need more observations and better models to really figure it all out. The Milky Way's rotation isn't uniform. You might think a galaxy rotates like a solid disk, with everything spinning at the same rate, but it doesn't. Different parts of the Milky Way rotate at different speeds. This is called differential rotation. Near the center, the rotation is fast. As you move outward, the rotation speed changes, and it doesn't follow the pattern you'd expect if the galaxy were just a collection of stars held together by gravity. If that were the case, stars farther from the center should move slower, just like planets in the solar system. The farther a planet is from the sun, the slower it orbits. But in the Milky Way, the rotation curve, which is a graph of rotation speed versus distance from the center, stays pretty flat out to large distances. This is actually one of the key pieces of evidence for dark matter. The flat rotation curve suggests there's a lot of invisible mass distributed throughout the galaxy, providing extra gravitational pull that keeps the outer stars wood. Without dark matter, the stars, at moving faster than they otherwise, the edge of the galaxy should be moving so slowly that they'd drift away. But they don't. They're held in place by the gravity of dark matter. So the rotation of the Milky Way tells us something fundamental about the universe. It's not just about how the galaxy spins, it's about what the galaxy is made of, and most of it is something we can't see. Differential rotation also has other effects. It causes the spiral arms to wind up over time. If the galaxy were rotating like a solid disk, the spiral arms would stay in place. But because different parts rotate at different speeds, the arms get stretched and twisted. This is called the winding problem, and it's one of the reasons why spiral arms are thought to be density waves rather than permanent structures. The arms aren't made of the same stars all the time. They're regions where stars and gas pile up temporarily as they move through the galaxy. It's like a traffic jam on a highway. The cars in the jam are always changing, but the jam itself stays in roughly the same place. In the same way, stars move in and out of the spiral arms, but the arms themselves persist as patterns in the galaxy's structure. At least that's the theory. There's still debate about exactly how spiral arms form and how long they last. Some simulations suggest they're transient features that come and go over hundreds of millions of years. Others suggest they're more stable. It probably depends on a lot of factors, including the amount of dark matter, the distribution of gas, and the history of interactions with other galaxies. The Milky Way has a thick disk in addition to the thin disk. Most of the stars we see in the night sky are part of the thin disk, which is, well, thin. Maybe 1,000 light years thick, but there's also a thick disk which extends several thousand light years above and below the plane of the galaxy. The thick disk contains older stars, and they're moving faster, in a more random way compared to the orderly rotation of the thin disk. The thick disk stars also have different chemical compositions. They have fewer heavy elements, which suggests they formed earlier in the galaxy's history, before multiple generations of stars had enriched the interstellar medium with metals. How the thick disk formed is a bit of a mystery. One idea is that it was created by the merger of the Milky Way with smaller galaxies in the past. When a small galaxy merges with a larger one, its stars get scattered and mixed into the larger galaxy's structure. Over time, these stars settle into a thick disk. Another idea is that the thick disk formed from the thin disk through a process called disk heating. Gravitational interactions, maybe with dark matter clumps or with spiral arms, can gradually increase the random motions of stars, puffing up the disk over time. Or maybe it's a combination of both processes. The thick disk might have started with some stars from mergers, and then more stars were added through disk heating. We're still figuring it out. Observations of the thick disk stars, their ages, their compositions, and their motions are helping to narrow down the possibilities. But it's complicated because the thick disk overlaps with the thin disk and the halo, and it's hard to tell them apart just by looking. The Milky Way is embedded in a halo of dark matter that extends far beyond the visible stars. This dark matter halo is spherical, or maybe slightly flattened, and it's much larger than the galaxy itself. It might extend out to 1 million light years or more. Most of the Milky Way's mass is in this halo, not in the stars and gas we can see. The dark matter doesn't emit light, doesn't absorb light, and doesn't interact with normal matter except through gravity. So we can't see it directly, we infer its presence from its gravitational effects, like the rotation curve we talked about earlier. The dark matter halo also affects the orbits of satellite galaxies, like the Magellanic Clouds. By studying how these satellites move, we can estimate the mass and shape of the halo. Some studies suggest the halo might be elongated, shaped more like a football than a basketball. Others suggest it's more spherical. The exact shape matters because it can tell us something about how dark matter behaves and how it's distributed. There are also smaller clumps of dark matter within the halo, called subhalos. These are the remnants of smaller dark matter halos that were absorbed when the Milky Way grew by merging with other galaxies. Some of these subhalos might still contain a few stars, forming the ultra-faint dwarf galaxies we've discovered. But most subhalos are probably completely dark, with no stars at all, just invisible clumps of dark matter drifting through the halo. It's a strange thought that most of the mass around us is invisible and unknown. The sun's path through the Milky Way isn't a perfect circle. It wobbles up and down as it orbits. The sun, like all stars in the disk, moves in an elliptical orbit around the galactic center, but it also oscillates above and below the plane of the disk. This vertical motion is caused by the gravitational pull of the disk itself. Imagine the disk as a thin sheet of mass. If the sun drifts above the plane, gravity pulls it back down. It overshoots, goes below the plane, and then gravity pulls it back up. This creates a bobbing motion, like a ball bouncing up and down on a spring. The sun crosses the plane of the galaxy roughly every 30 million years or so. Some researchers have speculated that these crossings might have effects on Earth, maybe triggering increased comet impacts or influencing G-climate. The idea is that when the sun passes through the denser part of the disk, gravitational interactions might disturb the Oort cloud, the distant reservoir of comets at the edge of the solar system, sending some of them into the inner solar system where they could hit Earth. There's also been speculation that passing through spiral arms, where there's more gas and dust, could affect the solar system in various ways. But these ideas are pretty controversial, and there's not much evidence to support them. The effects, if they exist at all, are probably very subtle. Still, it's interesting to think that our motion through the galaxy might have some influence on what happens here on Earth, even if it's just a tiny one. The Milky Way's disk is warped, not flat. If you could see the galaxy edge on, you'd notice that the outer parts of the disk don't lie in a perfect plane. They're bent like the brim of a hat. One side of the disk curves upward and the other side curves downward. This warp is most noticeable in the distribution of hydrogen gas, but it also affects the stars. Why is the disk warped? That's another question without a definite answer. One possibility is that it's caused by gravitational interactions with the Magellanic Clouds. The clouds are massive enough that their gravity can tug on the outer parts of the Milky Way's disk, pulling it out of shape. Another idea is that the warp is a result of the dark matter halo being slightly misaligned with the disk. If the halo is tilted or elongated, its gravitational pull might distort the disk. Or maybe the warp is left over from a past interaction with another galaxy, something that happened a long time ago and hasn't fully settled down yet. The warp changes over time, so it's a dynamic feature, not a permanent one. Observations are still being refined to figure out exactly how the warp is shaped and how it's evolving. It's one of those things that seems simple, just a bend in the disk, but turns out to be really complicated when you try to understand it. The Milky Way has streams of stars that are the remnants of destroyed galaxies. When a small galaxy gets too close to the Milky Way, tidal forces, the difference in gravitational pull across the galaxy, can tear it apart. The stars from the small galaxy get stretched out into a long stream that wraps around the Milky Way. Over time, these streams spread out and mix into the halo, but for a while, they remain as distinct structures that we can detect. The most famous example is the Sagittarius stream, the remnant of the Sagittarius dwarf elliptical galaxy, which is currently being torn apart by the Milky Way. The stream loops around the sky, a trail of stars that marks the path of the doomed galaxy. There are other streams too, discovered through careful surveys of the sky. Each stream tells a story of a small galaxy that wandered too close and met its end. By studying these streams, their positions, their velocities, their compositions, we can learn about the history of the Milky Way's growth. How many small galaxies has it consumed? When did these mergers happen? What were the properties of the galaxies that were destroyed? The streams are like fossils, preserving information about events that happened billions of years ago. And they're still out there, slowly fading into the background as they mix with the rest of the halo, but still visible if you know where to look. The Milky Way's central black hole is surprisingly quiet. Sagittarius A star, the supermassive black hole at the center of the galaxy, is massive, but it's not very active. It's not consuming a lot of material, so it's not shining brightly like the supermassive black holes in some other galaxies. Those active black holes, called active galactic nuclei, or AGN, are surrounded by disks of hot gas that emit huge amounts of light, sometimes outshining the entire galaxy. Sagittarius A star doesn't do that. It's relatively dim, which means it's not accreting much matter. Occasionally it flares up a bit, probably when a clump of gas or maybe a small object like an asteroid gets too close and falls in. But most of the time it's quiet. Why is it so quiet? Maybe there's just not much gas near the black hole to feed it. The central region of the galaxy is actually pretty empty, at least compared to the disk. Or maybe something is preventing gas from falling in. There could be outflows, winds of hot gas blown away by past activity that are keeping new material at bay. Or maybe the black hole is just going through a quiet phase, and it was more active in the past. There's some evidence that the Milky Way's center was more violent a few million years ago. We see signs of large-scale outflows, bubbles of hot gas extending above and below the plane of the galaxy, called the Fermi bubbles. These might have been created by a burst of activity from Sagittarius A star, or by a wave of star formation in the central region. But right now, things are calm. The Milky Way's center is also home to a cluster of massive stars. Very close to Sagittarius A star, within a few light years, there are dozens of young, hot, massive stars. These stars shouldn't be there. Massive stars form in dense gas clouds, but the environment near a supermassive black hole is extremely hostile. The tidal forces are strong, and there's a lot of radiation, It's not a place where you'd expect to find a nursery of young stars. So how did they get there? One idea is that they formed farther out and then migrated inward. Maybe they were part of a star cluster that spiraled toward the center due to dynamical friction, the drag caused by gravitational interactions with other stars and gas. Another idea is that they formed in a dense disk of gas that existed around the black hole in the past. If there was a lot of gas near the center, maybe it could have collapsed into stars despite the harsh conditions. Or maybe the stars formed in smaller clumps that then fell toward the black hole. It's a puzzle. And these stars are interesting for other reasons too. By watching how they orbit Sagittarius A star, we can measure the black hole's mass very precisely. One star, called S2, has an orbit that brings it extremely close to the black hole every 16 years. Observations of S2's motion have been used to test Einstein's theory of general relativity in a strong gravitational field. So far, the theory holds up, but these stars won't last forever. They're massive, so they burn through their fuel quickly. In a few million years, they'll explode as supernovae or collapse into black holes themselves. It'll be a spectacular show if anyone's around to watch. And if one of those explosions happens close enough to Sagittarius A star, it could actually feed the black hole. Maybe that's what will wake it up from its current quiet state. A supernova going off nearby, dumping a bunch of gas and debris onto the black hole. That could trigger a burst of activity, but for now, it's quiet, just sitting there, holding the galaxy together. The Milky Way also has something called a bar, not the kind you walk into, but a bar-shaped structure of stars running through the center of the galaxy. It's made up of old stars, and it extends for thousands of light years on either side of the nucleus. The bar rotates, and as it does, it helps funnel gas inward toward the center. This might be one reason why the central region has so many stars. The bar acts like a conveyor belt, pushing material toward the middle. But bars aren't unique to the Milky Way. Lots of spiral galaxies have them. Maybe most spiral galaxies have them, actually. We used to think barred spirals were less common, but now we know they're pretty typical. The bar might also affect the spiral arms. It can drive the formation of spiral structure by creating density waves, regions where stars and gas pile up as they orbit. These density waves propagate through the disk like ripples on water. Stars don't stay in the arms, they pass through them, but the arms themselves persist. It's a bit like a traffic jam. The cars move through, but the jam stays in the same place. The spiral arms might be created by the bar, or they might be caused by gravitational interactions with other galaxies, or maybe both. It's complicated. The Milky Way's spiral arms aren't even perfectly defined. They're kind of fuzzy, and different methods of tracing them give different results. Some arms are prominent in certain wavelengths, but not in others. Mapping the arms is hard because we're inside the galaxy. It's like trying to draw a map of a forest while standing in the middle of it. You can see trees nearby, but the overall shape is tough to figure out. The Milky Way has companion galaxies. Lots of them, actually. The largest ones are the Large Magellanic Cloud and the Small Magellanic Cloud. These are irregular dwarf galaxies visible from the southern hemisphere. They're orbiting the Milky Way, and they're close enough that their gravity is pulling on us. In fact, they might have played a role in shaping the Milky Way's disk. Some of the gas we see in the outer parts of the galaxy might have been stripped from the Magellanic Clouds as they passed by. There's a stream of gas called the Magellanic Stream trailing behind the clouds. It stretches for something like 600,000 light years. That gas might eventually fall into the Milky Way and fuel new star formation. The Magellanic Clouds themselves are interesting. The Large Magellanic Cloud has a bar, and it has regions of intense star formation. The Tarantula Nebula, one of the most active star-forming regions known, is in the Large Magellanic Cloud. If it were as close to us as the Orion Nebula, it would cast shadows on Earth. That's how bright it is. The Small Magellanic Cloud is less massive and less organized, but it's still a significant satellite. Both clouds are probably going to merge with the Milky Way eventually, not anytime soon. It'll take billions of years. But their orbits are decaying, and eventually they'll fall in. When that happens, it'll trigger a burst of star formation as their gas collides with ours. There are also dozens of smaller dwarf galaxies orbiting the Milky Way. Most of them are very faint, made up of old stars and not much else. Some of them might be the remnants of larger galaxies that were torn apart by the Milky Way's gravity. We've found streams of stars that seem to be the debris from these disrupted galaxies. The Milky Way has been cannibalizing smaller galaxies for its entire history. It's how big galaxies grow. They eat smaller ones. Speaking of mergers, the Milky Way is on a collision course with the Andromeda Galaxy. Andromeda is the nearest large spiral galaxy, about 2.5 million light-years away. It's bigger than the Milky Way, maybe twice as massive, and it's heading toward us. The two galaxies are moving toward each other at something like 110 kilometers per second. In about 4 to 5 billion years, they'll collide. Now, when galaxies collide, it's not like stars crash into each other. Space is mostly empty, so the stars will just pass by each other. But the gas clouds will collide, and that'll trigger massive bursts of star formation. The two galaxies will merge into one giant elliptical galaxy. People have called it Milkomeda, which is a terrible name, but it's catchy. The night sky will look very different during the merger. For a while, Andromeda will dominate the sky, much larger and brighter than it is now. Then the two galaxies will start to distort each other, their spiral arms pulled out by tidal forces. Eventually, they'll blend together into a single, chaotic system. Stars will be thrown into new orbits. Some will be flung out into intergalactic space. The supermassive black holes at the centers of both galaxies will spiral toward each other and eventually merge, creating an even larger black hole and releasing a pulse of gravitational waves. The Sun, if it's still around, will probably survive the merger. It'll be thrown into a different orbit, maybe farther from the center, maybe closer. Earth might survive too, though by that time the Sun will be nearing the end of its life, so it might not matter. The merger will take a long time, hundreds of millions of years. The galaxies will pass through each other, then swing back, then pass through again. Each time they'll lose energy and get closer until finally they settle into a single system. It's one can happen to a galaxy of the most dramatic events and it's going to happen to ours. But the Milky Way isn't just colliding with Andromeda, it's also interacting with the Triangulum Galaxy, another member of the local group. Triangulum is smaller than the Milky Way or Andromeda, but it's close enough that it might get caught up in the merger, or it might have already interacted with Andromeda in the past. There's some evidence that Triangulum's structure has been disturbed by gravitational interactions. The local group is a cluster of about 80 galaxies, most of them small dwarfs. The Milky Way and Andromeda are the two dominant members. They're both pulling on the smaller galaxies around them. Some of those galaxies will eventually fall into one or the other. It's a slow process, but it's ongoing. The local group is part of a larger structure called the Virgo supercluster, which is itself part of an even larger structure called Laniakea. These are the cosmic web structures we talked about earlier. The Milky Way is moving through space, pulled by the gravity of these larger structures. We're falling toward the Virgo cluster, a massive collection of galaxies about 50 million light years away. But we're also being pulled in other directions by other concentrations of mass. The universe is full of these flows, galaxies moving through space along invisible rivers of gravity. The Milky Way is surrounded by something called the circumgalactic medium, a halo of hot gas extending far beyond the visible disk. This gas is very diffuse, but there's a lot of it, maybe as much mass in the circumgalactic medium as there is in all the stars in the galaxy. The gas is mostly hydrogen, and it's very hot, millions of degrees. It's left over from the galaxy's formation, or it's been ejected from the disk by supernova explosions and stellar winds. The circumgalactic medium is hard to study because it's so faint, but it's important. It's a reservoir of material that could eventually fall back into the galaxy and form new stars. It's also the interface between the galaxy and the intergalactic medium, the even more diffuse gas that fills the space between galaxies. Gas flows in and out of the circumgalactic medium, connecting the galaxy to the larger universe. Some of that gas might have come from other galaxies, carried by winds or stripped away by tidal forces. The Milky Way is not a closed system. It's constantly exchanging material with its surroundings. The disk of the Milky Way is thin, but it's not flat. It's warped. If you could see it edge on from far away, you'd notice that the outer parts of the disk are bent, tilted up on one side and down on the other. This warp is probably caused by gravitational interactions with the Magellanic Clouds or other satellite galaxies. The warp changes over time as the satellites orbit and the disk responds. The disk also has a flare. The farther out you go, the thicker the disk gets. This might be because there's less gravity holding it together out there, so random motions of stars spread it out. Or it might be due to interactions with dark matter or satellite galaxies. The structure of the Milky Way is constantly being shaped by forces both internal and external. There are also streams of stars moving through the galaxy, remnants of smaller galaxies or star clusters that were torn apart by the Milky Way's gravity. These streams are like rivers of stars, all moving in the same direction because they came from the same source. By studying these streams, we can learn about the Milky Way's gravitational field and about the history of its interactions with other galaxies. Some streams are very old, their stars spread out over large regions of the sky. Others are younger and more compact. The most famous stream is probably the Sagittarius stream, which comes from the Sagittarius dwarf elliptical galaxy. This galaxy is currently being torn apart by the Milky Way, and its stars are being spread out into a long stream that wraps around the galaxy. In a few billion years, the Sagittarius dwarf will be completely destroyed, its stars absorbed into the Milky Way. The Milky Way also has globular clusters. These are dense, spherical collections of stars, much older than the open clusters we see in the disk. Globular clusters orbit the galaxy in the halo, the region above and below the disk. There are about 150 known globular clusters in the Milky Way, but there might be more that we haven't found yet. Each cluster contains hundreds of thousands of stars, all packed into a region only a few dozen light years across. The stars in globular clusters are very old, some of the oldest stars in the galaxy. They formed early in the Milky Way's history, maybe even before the disk fully formed. Studying globular clusters can tell us about the conditions in the early universe. The stars in these clusters have very low metallicity, meaning they contain very few elements heavier than hydrogen and helium. That's because they formed before many generations of stars had lived and died, before the universe had been enriched with heavy elements. Globular clusters are also interesting because they're very stable. They've survived for billions of years without being torn apart. That's partly because they're so dense. The gravity holding them together is strong enough to resist tidal forces from the galaxy. But it's also because they orbit in the halo, where there's less matter to disrupt them. The disk of the Milky Way also contains a lot of open clusters, which are different from globular clusters. Open clusters are younger, loosely bound groups of stars that form together from the same molecular cloud. They're usually found in the spiral arms, where star formation is still happening. Open clusters don't last as long as globular clusters because they're not as tightly bound. Over time, interactions with other objects in the galaxy can pull them apart, and their stars disperse into the general population of the disk. Some open clusters are only a few million years old, while others are a few billion years old. The Pleiades is probably the most famous open cluster, visible to the naked eye as a small group of bright stars. It's relatively young, only about 100 million years old, and it contains hot, blue stars that haven't had time to evolve into red giants yet. There are thousands of open clusters in the Milky Way, though we've only cataloged a fraction of them. Many are hidden behind dust clouds or are too faint to see easily. But they're important for understanding star formation and the chemical evolution of the galaxy. Because all the stars in an open cluster formed at the same time from the same material, they have the same age and composition. That makes them useful for testing models of stellar evolution. You can compare stars of different masses in the same cluster and see how they evolve differently. The spiral arms of the Milky Way are where most of the star formation happens. These arms are density waves, regions where matter piles up temporarily as it orbits the galaxy. Stars and gas clouds move through the spiral arms, but the arms themselves don't rotate like solid objects. Instead, they're patterns that persist even as the material flows through them. It's kind of like a traffic jam on a highway. The cars move through the jam, but the jam itself stays in roughly the same place. When gas clouds enter a spiral arm, they get compressed by the increased density, and that compression can trigger the collapse of the cloud and the formation of new stars. That's why spiral arms are bright. They're full of young, hot stars that light up the gas around them. The exact number of spiral arms in the Milky Way has been debated for a long time. Some models say there are 2 major arms, others say 4. It's hard to map the arms accurately because we're inside the galaxy and dust blocks our view in many directions. But by studying the distribution of young stars, molecular clouds, and other tracers of spiral structure, astronomers have pieced together a rough map. The arms are named after the constellations they pass through when viewed from Earth. There's the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm. The Sun is located in a smaller structure called the Orion Spur, which is sort of a bridge between 2 of the major arms. The Milky Way is also home to a lot of nebulae, which are clouds of gas and dust. Some nebulae are emission nebulae, glowing because the gas inside them is ionized by nearby hot stars. The Orion Nebula is a famous example. It's a stellar nursery, a place where new stars are being born right now. You can see it with the naked eye as a fuzzy patch in the constellation Orion. Other nebulae are reflection nebulae, which don't emit their own light but reflect the light of nearby stars. They're usually blue because blue light scatters more easily. And then there are dark nebulae, which are dense clouds that block the light from stars behind them. The Horsehead Nebula is a well-known dark nebula, silhouetted against a brighter background. These nebulae are the raw material for future stars. Over millions of years, parts of them will collapse under their own gravity, fragment into smaller clumps, and eventually form new stars and planets. The cycle of star formation and death is ongoing in the Milky Way. Old stars die and return their material to space, enriching the interstellar medium with heavy elements. That material then gets incorporated into new stars, which eventually die and return their material to space, and so on. The interstellar medium itself is a complex, multi-phase environment. It's not just empty space, it's filled with gas at different temperatures and densities, dust grains, cosmic rays, and magnetic fields. There's cold molecular gas, where temperatures are only a few degrees above absolute zero. There's warm, neutral gas with temperatures around a few thousand degrees. There's warm, ionized gas, heated by stars, and hot, ionized gas, heated by supernova explosions with temperatures in the millions of degrees. These different phases coexist and interact with each other. Supernova shock waves plow through the interstellar medium, creating bubbles of hot gas that can be hundreds of light years across. Stellar winds from massive stars push gas around, carving out cavities. Magnetic fields thread through the gas, affecting how it moves and collapses. Cosmic rays, high-energy particles accelerated by supernovae and other energetic events permeate the galaxy and can influence star formation by heating the gas. The interstellar medium is constantly being stirred and mixed by all these processes, and it's this dynamic environment that sets the stage for star formation. The Milky Way also has a lot of dark matter, though we can't see it directly. We know it's there because of its gravitational effects. The rotation curve of the galaxy, the way the speed of stars changes with distance from the center, doesn't match what we'd expect if only the visible matter were present. Stars far from the center are moving faster than they should be, which means there must be additional mass out there holding them in their orbits. That additional mass is dark matter. It's distributed in a roughly spherical halo around the galaxy, extending far beyond the visible disk. The dark matter halo might contain 10 times as much mass as all the visible matter in the Milky Way combined. Maybe even more. We don't know what dark matter is made of. It doesn't emit light, doesn't absorb light, doesn't interact with normal matter except through gravity. There are lots of theories, but no confirmed detections yet. Some scientists think it's made of exotic particles that were created in the early universe. Others have proposed modifications to gravity that could explain the observations without needing dark matter. But for now, dark matter remains one of the biggest mysteries in astrophysics. The Milky Way is constantly interacting with its satellite galaxies. These are smaller galaxies that orbit the Milky Way, bound by its gravity. The most famous are the large and small Magellanic Clouds, which are visible from the southern hemisphere as faint, cloudy patches in the sky. They're irregular dwarf galaxies, much smaller than the Milky Way, but still containing billions of stars. The Magellanic Clouds are slowly being pulled apart by the Milky Way's gravity. There's a stream of gas called the Magellanic Stream that's been stripped from them and now stretches across a large portion of the sky. In the future, maybe in a few billion years, the Magellanic Clouds will probably be completely absorbed into the Milky Way. There are dozens of other satellite galaxies too, most of them much smaller and fainter. Some are so small and dim that they're hard to distinguish from globular clusters. These ultra-faint dwarf galaxies are interesting because they're thought to be some of the most dark, matter-dominated objects in the universe. They contain very few stars, but a lot of dark matter, which is the only thing holding them together. Studying these satellites helps us understand how galaxies form and evolve, and how dark matter behaves on small scales. The history of the Milky Way is written in its stars. By studying the ages, compositions, and motions of stars, astronomers can piece together the galaxy's past. The oldest stars, found in the halo and in globular clusters, are more than 13 billion years old. Formed not long after the Big Bang, they're metal poor, meaning they contain very few heavy elements, because the universe hadn't yet been enriched by many generations of stars. The disk is younger, maybe 10 billion years old or so, and its stars have higher metallicity. The spiral arms are even younger, with ongoing star formation producing stars that are only a few million years old. The Milky Way probably formed through a process of hierarchical assembly, where smaller structures merged together to form larger ones. In the early universe, small clumps of dark matter collapsed and pulled in gas, forming the first stars and galaxies. Over time, these small galaxies collided and merged, building up larger galaxies like the Milky Way. Evidence for this process can be seen in the streams of stars we talked about earlier, which are the remnants of smaller galaxies that were torn apart. The Milky Way has been eating other galaxies for billions of years, and it's still doing it today. In the future, the Milky Way will continue to evolve. Star formation will probably continue for a long time, maybe tens of billions of years, though the rate might slow down as the galaxy uses up its gas. The most dramatic event in the Milky Way's future will be its collision with the Andromeda Galaxy. Andromeda is currently moving toward us at about 110 kilometers per second, and in about 4 billion years, the two galaxies will collide. It won't be a violent collision in the sense of stars crashing into each other, because the distances between stars are so vast that actual collisions will be extremely rare. But the gravitational interactions will completely reshape both galaxies. The disks will be disrupted, stars will be flung into new orbits, and the two supermassive black holes at the centers will eventually merge. The result will be a new, larger galaxy, probably an elliptical galaxy that astronomers have nicknamed Milkomeda. The Sun and Earth will probably survive the merger, though we'll end up in a very different part of the new galaxy. By that time, the Sun will be nearing the end of its life anyway, so life on Earth will have other problems to worry about. The Milky Way is also part of a larger structure called the Local Group, which is a collection of more than 50 galaxies bound together by gravity. The Milky Way and Andromeda are the two largest galaxies in the Local Group, and most of the others are small dwarf galaxies orbiting one or the other. The Local Group itself is part of an even larger structure called the Virgo supercluster, which contains thousands of galaxies spread over a region about 110 million light-years across. And the Virgo supercluster is part of an even larger structure called Laniakea, which contains about 100,000 galaxies. These structures are shaped by gravity. Galaxies cluster together because of their mutual gravitational attraction, and the clusters themselves are organized into larger filaments and sheets separ aided by vast voids. The universe on the largest scales looks like a cosmic web, with galaxies concentrated along the filaments and relatively empty space in between. The Milky Way is just one tiny part of this immense structure, moving through space along with everything else. Understanding where the Milky Way fits into this cosmic web helps put things in perspective, maybe. Like, we're not just sitting here in isolation. The galaxy is moving. We're all moving. The Milky Way itself is moving through space at about 600 kilometers per second relative to the cosmic microwave background, which is the leftover radiation from the Big Bang. That's over 2 million kilometers per hour. You're moving through space right now at millions of kilometers per hour, and you can't even feel it. Everything's moving. The Earth orbits the Sun orbits the center of the galaxy moves through the local group, and the local group moves through the larger structures of the universe. It's motion all the way down. Or up. Both, really. And all of this motion is driven by gravity, the same force that keeps you stuck to the ground. Gravity shapes everything on the largest scales. It's why galaxies cluster together, why the cosmic web exists, why the Milky Way and Andromeda are on a collision course. Gravity is weak compared to the other fundamental forces, but it's the only one that matters at cosmic distances because it always attracts and it never cancels out. Electromagnetism can be attractive or repulsive, so large objects tend to be electrically neutral. But gravity only pulls, so the more mass you have, the stronger the pull. Over billions of years, that pull has organized the universe into the structures we see today. One of the stranger things about the Milky Way's motion is that it's not entirely explained by the gravity of the visible matter around us. The local group is being pulled toward a region called the Great Attractor, which is a massive concentration of galaxies about 150 million light-years away. But even the Great Attractor doesn't fully explain our motion. There's something even larger pulling us in a slightly different direction, a structure called the Shapley supercluster, which is one of the largest concentrations of galaxies in the observable universe. We're being pulled by structures so massive and so distant that we can barely map them, and the Milky Way is just going along for the ride. It's humbling, sort of. We like to think of ourselves as the center of things, but we're not even close. We're on the outskirts of a medium-sized galaxy, in a small group of galaxies, on the edge of a supercluster, being pulled by forces we're only beginning to understand. The Milky Way also interacts with its environment in other ways. For example, there's something called the galactic halo, which is a roughly spherical region of space surrounding the galaxy. The halo contains globular clusters, those ancient balls of stars we talked about earlier, but it also contains dark matter. In fact, most of the Milky Way's mass is probably in the halo, in the form of dark matter. We can't see it directly, but we can infer its presence from the way it affects the motion of stars and gas in the outer parts of the galaxy. The rotation curve of the Milky Way, which is a graph showing how fast stars orbit at different distances from the center, stays flat even very far from the center. That shouldn't happen if the only mass in the galaxy is the stuff we can see. The rotation speed should drop off as you get farther from the center, like the way planets farther from the sun orbit more slowly. But it doesn't drop off, which means there must be a lot of invisible mass out there, holding everything together. That mass is dark matter, probably. We don't know what dark matter is made of, but we know it's there because of its gravitational effects. It's one of the biggest mysteries in astrophysics, and the Milky Way is one of the best places to study it because we're inside it and can make detailed measurements. The halo also contains something called high-velocity clouds, which are clumps of gas moving through the halo at speeds that don't match the rotation of the disk. Some of these clouds are probably gas that was stripped from satellite galaxies as they passed through the Milky Way. Others might be gas that was ejected from the disk by supernova explosions or other energetic events, and is now falling back down. These clouds are important because they can bring fresh gas into the disk, fueling new star formation. The Milky Way is constantly recycling material, pulling in gas from its surroundings, and using it to make new stars. It's a cycle that's been going on for billions of years and will probably continue for billions more. Another interesting feature of the Milky Way is its magnetic field. The galaxy has a large-scale magnetic field that threads through the disk and the halo. This field is probably generated by the motion of charged particles in the gas and plasma that fills the galaxy, kind of like how Earth's magnetic field is generated by the motion of molten iron in the core. The Milky Way's magnetic field affects the motion of cosmic rays, which are high-energy particles, mostly protons, that zip through the galaxy at nearly the speed of light. Cosmic rays are produced by supernova explosions and other violent events, and they travel along the magnetic field lines, getting trapped and bouncing around. The magnetic field also affects how gas moves and collapses to form stars. It can provide support against gravity, slowing down the collapse, or it can channel gas along field lines, creating structures. Magnetic fields are really hard to study because they're invisible, and you can only detect them indirectly by looking at how they affect other things, like the polarization of light or the motion of charged particles. But they're an important part of how galaxies work. The Milky Way is also a source of various types of radiation across the electromagnetic spectrum. In visible light, we see the stars. In infrared, we see cooler objects like dust clouds and red giants. In radio waves, we can see the emissions from neutral hydrogen gas and from pulsars and supernova remnants. In X-rays, we see the hottest and most energetic phenomena like the regions around black holes and neutron stars. And in gamma rays, the highest energy form of light, we see emissions from cosmic ray interactions and possibly from dark matter annihilation, though that last one is still uncertain. By observing the Milky Way in all these different wavelengths, astronomers can build up a complete picture of what's going on. Each wavelength reveals different aspects of the galaxy, and you need all of them to really understand it. There's also the question of what the Milky Way looks like from the outside. We can't leave the galaxy and take a picture of it, obviously, so we have to rely on observations of other spiral galaxies that are similar to ours. Based on those observations and on detailed measurements of the structure of the Milky Way from the inside, astronomers have been able to create models and simulations of what the galaxy would look like if we could see it from a distance. These models show a beautiful spiral galaxy with a bright central bulge, sweeping spiral arms, and a faint halo of stars and globular clusters surrounding it. It would probably look a lot like the Andromeda galaxy, which is our nearest large neighbor and is also a spiral galaxy. Andromeda is about 2.5 million light-years away, and it's actually visible to the naked eye from a dark location as a faint smudge of light. That's the farthest thing you can see with your unaided eyes, the light from a galaxy millions of light-years away. When you look at Andromeda, you're seeing what the Milky Way might look like from the outside. One of the most fascinating aspects of studying the Milky Way is that we're part of it. We're not external observers looking in from a distance. We're embedded in the structure, surrounded by stars and gas and dust. This makes some things easier because we can study individual stars and gas clouds in great detail. But it also makes some things harder because we can't see the big picture. It's like trying to understand the layout of a city when you're standing in the middle of it versus looking at a map from above. Both perspectives have their advantages, and astronomers use both by studying the Milky Way from the inside and by studying other galaxies from the outside and comparing them. The combination of these approaches has given us a pretty good understanding of our galaxy, though there are still plenty of mysteries left to solve. The center of the Milky Way is a particularly interesting region. We've talked about Sagittarius A star, the supermassive black hole at the very center, but there's a lot more going on there. The central region of the galaxy is incredibly crowded with stars. In the innermost light year around Sagittarius, a star, there are millions of stars packed together, with densities thousands of times higher than in the Sun's neighborhood. Some of these stars are in very close orbits around the black hole, taking only a few years to complete one orbit. By tracking the motion of these stars over time, astronomers have been able to measure the mass of the black hole very precisely. One of these stars, called S2, orbits the black hole every 16 years, and its orbit has been tracked for decades. The observations of S2 and other stars near the black hole have confirmed predictions from Einstein's theory of general relativity, like the way time slows down in strong gravitational fields and the way light is bent by gravity. The center of the Milky Way is one of the best natural laboratories for testing these extreme physics theories. The central region also contains a lot of gas and dust, and there's evidence of recent star formation there, which is surprising because the environment is so chaotic and violent. The tidal forces from the black hole and the intense radiation from nearby stars should make it hard for gas clouds to collapse and form stars, but somehow it's happening anyway. There are also structures called the Fermi bubbles, which are giant lobes of high-energy gamma rays extending above and below the galactic plane from the center. These bubbles are huge, each about 25,000 light-years across, and they were only discovered in 2010 by the Fermi Gamma Ray Space Telescope. The origin of the Fermi bubbles is still debated, but they might be the result of a burst of activity from Sagittarius A star in the past, maybe a few million years ago when the black hole was actively feeding and blasting out jets of energy. Or they could be the result of intense star formation and supernova explosions, in the central region. Either way, they're evidence that the center of the galaxy is a dynamic and energetic place, not a quiet and stable one. Another mystery related to the center of the Milky Way is the so-called missing satellites problem. Computer simulations of galaxy formation predict that a galaxy like the Milky Way should have hundreds or even thousands of small satellite galaxies orbiting around it. But we only see a few dozen. Where are the rest? One possibility is that they're out there, but they're too faint to detect. Dwarf galaxies can be incredibly dim, made up mostly of dark matter with only a few stars, and they might be invisible with current telescopes. Another possibility is that the simulations are wrong, or that they're missing some important physics that affects how small galaxies form and survive. This is an active area of research, and new surveys that can detect very faint objects are starting to find more and more of these tiny satellite galaxies. So maybe the missing satellites aren't missing after all, just hidden. It's also possible that many of the predicted satellites were disrupted and torn apart by the Milky Way's gravity, leaving behind only streams of stars like the ones we've detected. The answer probably involves a combination of all these factors. The Milky Way is also home to a variety of exotic objects and phenomena that we're still trying to understand. There are neutron stars, which are the collapsed cores of massive stars, so dense that a teaspoon of neutron star material would weigh billions of tons. There are pulsars, which are rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. There are magnetars, which are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. There are black holes of various sizes, from stellar mass black holes formed by the collapse of massive stars to the supermassive black hole at the center. There are supernova remnants, the expanding shells of gas and dust left behind by exploding stars. There are planetary nebulae, the glowing shells of gas ejected by dying stars like the sun. And there are probably objects and phenomena that we haven't discovered yet, things that are too faint or too rare or too strange for us to have noticed so far. Every new telescope and every new survey reveals more surprises. The Milky Way is full of things we haven't even seen, things that are rare, things that probably began to figure out, things that are exist but we can't see them yet. Every time we point a new telescope at the sky, we find something unexpected, something that doesn't fit the models, something that makes us go back and rethink what we thought we knew. And that's kind of exciting, actually. It means the galaxy is still full of mysteries, still full of surprises. It's not like we've mapped everything and cataloged everything, and now we're just filling in the details. We're still in the early stages of exploration, still discovering fundamental things about how the Milky Way works. One thing that's been puzzling astronomers for a while is the fact that the Milky Way seems to be missing a lot of the ordinary matter that should be there. When you add up all the stars and gas and dust that we can see, it only accounts for a fraction of the normal matter that should exist based on the amount of dark matter and the way the galaxy formed. So where's the rest? It's not just dark matter, because dark matter is something else entirely. This is regular matter, protons and neutrons and electrons, the stuff that makes up atoms. It should be there, but we can't find it. The leading theory is that it's in the form of hot, diffuse gas that's spread out in a huge halo around the galaxy. Too hot and too thin to emit much light, but still there. This hot gas would be at temperatures of millions of degrees, so hot that it doesn't emit visible light, but instead glows in X-rays and ultraviolet. And detecting it is really hard because it's so spread out and so faint. But there are some hints from observations, some indirect evidence that it's there. If this hot halo exists, it would contain a huge amount of mass, maybe as much as all the stars in the Milky Way combined. And it would play an important role in the galaxy's evolution because gas from this halo could cool down and fall into the disk, where it would form new stars. So the hot halo might be a kind of reservoir of raw material for future star formation. But we don't know for sure. It's still mostly speculation based on models and indirect observations. Another weird thing about the Milky Way is that it seems to have had a pretty violent past. The galaxy wasn't always the calm, stable spiral we see today. It's been through collisions and mergers with other galaxies, and those events have left their mark. In fact, some of the stars in the Milky Way didn't form here at all. They formed in smaller galaxies that were later absorbed by the Milky Way. And now they're part of our galaxy, but they're still moving in weird orbits that reflect their origins. Astronomers can identify these interloper stars by looking at their chemical compositions and their motions, and they've found that a significant fraction of the stars in the halo, maybe as much as half, came from other galaxies. There's one dwarf galaxy in particular, called the Sagittarius Dwarf Elliptical Galaxy, that's currently being torn apart by the Milky Way's gravity. It's on the far side of the galaxy from us, but streams of stars from this galaxy have been stretched out all around the Milky Way, forming long arcs of stars that are slowly being absorbed. Eventually, all the stars from the Sagittarius dwarf will be completely mixed into the Milky Way, and the dwarf galaxy will cease to exist as a separate object. This process has probably happened many times in the past, with other small galaxies being swallowed up and digested by the Milky Way. So the Milky Way is kind of a cannibal galaxy, growing by eating its smaller neighbors. And that's the Milky Way, our home galaxy, this massive spiral of stars and gas and dust and dark matter that we're embedded in, that we're part of, that we're still trying to understand. We've learned an enormous amount about it in the last century. We've mapped its structure, measured its mass, tracked the motion of stars around the central black hole, discovered its satellites and streams and bubbles. We know it's about 13 billion years old, give or take. We know it has hundreds of billions of stars. We know it's on a collision course with Andromeda. We know it's full of dark matter that we can't see but can measure through its gravitational effects. We know the center is a chaotic, crowded place with a supermassive black hole and millions of stars packed into a tiny region. We know the disk is thin and warped and threaded with spiral arms where stars are being born right now. We know the halo is full of ancient stars and globular clusters and probably a lot of dark matter. We know the galaxy is surrounded by a halo of hot gas and satellite galaxies and streams of stars from galaxies that were torn apart long ago. But there's still so much we don't know. We don't know exactly how old the galaxy is or exactly how many stars it has. We don't know how the spiral arms form or how long they last. We don't know what dark matter is made of, even though it makes up most of the galaxy's mass. We don't know where all the ordinary matter is hiding. We don't know if there are thousands of black holes at the center or just a few dozen. We don't know how the supermassive black hole formed or why it's so quiet. We don't know if there are other intelligent civilizations out there somewhere in the galaxy. We don't know how the magnetic field is generated or maintained. We don't know why the disk is warped or why the halo extends so far. We don't know how the galaxy will evolve over the next few billion years, except that it's going to collide with Andromeda eventually, and that'll be spectacular. The Milky Way is enormous and ancient and complex, and we're only just starting to understand it. Every observation, every measurement, every new telescope reveals more details, more structure, more mysteries. And that's the thing about science, right? It's not about having all the answers. It's about asking better questions. It's about being curious. It's about looking up at the night sky and wondering what's out there, beyond what we can see, beyond what we know. The Milky Way is our cosmic home, but it's also a mystery, a puzzle that we're slowly piecing together, one observation at a time. And maybe that's fitting. Maybe it's good that we don't have all the answers yet. Maybe the mystery is part of what makes it beautiful. So tonight, as you drift off to sleep, you can think about the fact that you're part of something vast and ancient. You're made of atoms that were forged in stars billions of years ago, scattered across space by supernova explosions, eventually coming together to form the Earth and everything on it, including you. You're living on a planet orbiting a star in the disk of a spiral galaxy that's moving through space at millions of kilometers per hour. Part of a local group, part of a supercluster, part of a cosmic web of structure that stretches across the observable universe. and all around you, invisible but ever present, is dark matter holding everything together, mysterious and unknown. The Milky Way is full of wonders, it's full of questions, and we're lucky enough to be here right now, in this moment of history when we're just beginning to understand it. There's so much more to discover, so much more to learn, and maybe one day we'll answer all these questions, or maybe we'll just find new ones. Either way, the journey continues, the mystery remains, and the galaxy keeps spinning, carrying us along with it through the darkness and the light.